Welcome back to the next lecture. In this lecture, we are going to continue a discussion of dx by dt is equal to sin x, and we are going to use the phase portrait that we drew in the previous lecture and understand how x changes with time for a system that follows dx by dt equal to sin x. So, this is the system we have been studying. Notice this is a system with indefinite number of fixed points, but they are very reliable because the stability of the fixed points alternate. So, to make it easier for me, I am going to look at a very limited domain, very limited neighborhood on x axis in this phase portrait to draw x versus time diagram. So, I am going to limit myself from this fixed point to this one. So, from minus 2 pi to 2 pi. So, I am going to use this phase portrait to draw the diagram. Now, if you remember what we learned in the previous lecture, use the sign of dx by dt, whether it is positive or negative, to figure out the stability of the fixed point. So, here we have positive, negative, positive, negative. So, this fixed point is a stable one, unstable one, and then this one is also a stable fixed point. So, let us say I am starting at x equal to 0, x naught is x equal to 0, x equal to 0 is a fixed point, which means if I am starting here, the x will always remain 0 for all time to come. Now, let us start with x slightly bigger than 0. So, we are starting here, x is slightly bigger than 0, but still quite less than pi. Notice dx by dt here is positive, so x will increase. As x increases and approaches pi by 2, dx by dt continues to increase. So, here the slope will keep on increasing. So, this is curving upwards. As x increases beyond pi by 2, between pi by 2 and pi, what will start happening is that dx by dt is still positive, because notice this part of the curve is still positive, but the magnitude will start reducing. So, instead of accelerating, it is now decelerating. So, we will see a behavior that is actually quite similar to what we saw in case of logistic equation. So, it will start slowing down, and as it approaches pi here, which is a fixed point, a stable fixed point, dx by dt will start approaching 0, which means the curve will start flattening out. And it is an asymptote, which means at time t equal to infinity, for a starting position here, x naught 1 here, x will finally tend to pi. So, this means for the starting position here at x naught 1, as time tends to infinity, the x will come here at this line, which is equal to when x is equal to pi. So, asymptote here. Now, let us start from very close to the second fixed point. So, I am calling the fixed point as this, the first, the second, and then I will call this one, let us say -1 fixed point. So, when the fixed point is very close, when we are starting from the initial value that is very close to the second fixed point, let us say here, this is our x naught 2. Then what happens? Dx by dt is still positive. Look at here, dx by dt is still positive. So, the x is still going to increase, but as it increases and as it approaches pi, it will start slowing down. So, basically the curve will increase, but ever decelerating. Again, something that should remind you of what we saw in logistic equation. Now, what happens when we start right next to the pi on the positive side? So, we are slightly above pi. Again, notice very clearly dx by dt is negative. The sign of dx by dt is very important. So, let us say this is our x naught 3, we are starting here, x naught 3, we are close to the pi, but we are bigger than pi. Dx by dt is negative, which means that x will reduce. So, x is reducing. What happens as x reduces? It moves towards left side. The flow here is already towards left side. As it moves towards left side, the magnitude of dx by dt starts decreasing. So, it is the value of x is going to reduce, but the rate at which it is reducing will start slowing down. So, here it will be asymptote to this horizontal line, which is the line of fixed point. Now, what happens if we are starting at the fixed point? So, let us call it x naught 4. at the fixed point. Take a moment to think about it. Alright students, I hope you figured out, if you are starting at a fixed point, you stay at the fixed point. So this is how your trajectory looks like. Now similarly, you can draw what's going to happen on the negative side. It's actually going to be very similar to what we see here in the positive side, as these two are mirror images of each other. So I'm not going to draw this, but this is something that I encourage you to practice. Okay, now I want to look at some examples, other examples to help you find fixed points and stability of fixed points before I teach you other models. And the models I'm going to cover this week are all one-dimensional models. But first, let's do some exercises. The first exercise we are going to do is dx by dt. So we are going to look at a model dx by dt, x minus cos x. Now, the first step in any analysis for fixed point involves finding the fixed points. So remember, to find the fixed points, dx by dt has to be equal to 0. So when is dx by dt equal to 0? You can do this analytically, find out when x is close to cos x, calculate it, use series expansion or other methods that are available to us in mathematics. But remember, we are using a graphical approach. So we want to avoid the analytical calculations as far as possible. So what we are going to do instead is we are going to plot two curves x and cos x, and since they are minus, they are subtracting from each other, cos x is subtracting from x, we will use a relationship between the curves to understand how x minus cos x will work. So let's do this. We are first drawing the face portrait. On x-axis we have x, and on y-axis we have dx by dt. dx by dt equal to x minus cos x can also be treated as function 1, can also be treated as the first function minus second function, where first function is x and the second function is cos x. So let's plot first function, which is x. Now let's plot the second function. So now I have drawn cos x and x, and I am not very good at drawing graphs, but this should give you a fair approximation of what behavior to expect. Now here is the thing, whenever x is less than cos x, this function dx by dt is going to be negative. Whenever x is less than cos x, dx by dt is going to be negative. Whenever x is greater than cos x, dx by dt is going to be positive. Whenever they are equal, they are going to be 0. dx by dt is going to be 0. So, where are they equal in this graph? They are equal at the intersection point. So, here I know I have my fixed point. On the right side of the fixed point, x is greater than cos x, which is this situation. On the right side of this fixed point, x is greater than cos x, which is this situation. So dx by dt is positive, so the flow here is on right side. On left side, the flow here is on left side towards minus infinity because x is less than cos x, which is this situation. So even without finding out the precise point where x and cos x meet, where x minus cos x is equal to 0, by plotting these two graphs separately, I can find out roughly where the fixed point is and how the behavior around the fixed point is. And also the stability of this fixed point. Notice the arrows are moving away from the fixed point. So this is an unstable fixed point. Let's take another example. The second example looks like a very simple quadratic equation, 4x squared minus 16. The first step is find the fixed point. How are you going to do it? Dx by dt equal to 0. Now in this case, you can use the basic algebra that you learn in school. And then make it equal to 0. You know here that this system will be equal to 0 only when x is equal to either plus 2 or minus 2. So how many fixed points do you have here? You have 2 fixed points. So to draw your face portrait, on x-axis we place x, which is a variable, and on y-axis we place the rate at which the variable is changing, which is dx by dt. We know we have 2 fixed points, one is minus 2 and the other is plus 2. So at these 2 points, dx by dt is 0. Now we need to plot the dx by dt. And I remember in lecture number 3, I told you that one way to plot this is to look at the sign between and around the fixed point, the sign of dx by dt. So let's look at what happens when x is between these two fixed points. What is the sign of dx by dt? It's very convenient to take the x equal to 0. When x is equal to 0, which is when x is between minus 2 and 2, dx by dt is equal to minus 16, which is less than 0. So we know that 4x square minus 16 is going to be negative between these two fixed points. What happens when x is greater than 2? When x is greater than 2, dx by dt is going to be positive. What happens when x is less than minus 2? Once again, it's going to be positive. So the curve looks something like this. Now let's figure out the stability of these two fixed points. The first fixed point, minus 2. On left side, dx by dt is positive, which means x is increasing. So the flow of x is towards right. On right side of this fixed point, dx by dt is negative, which means x is reducing. So the flow of x is towards the left side. And the same will be true on the right side of the y-axis, because there is no fixed point between them. On the right side of the second fixed point, dx by dt is positive, which means x is increasing. So the flow is towards positive infinity, right side. Look at the direction of arrows. It should be pretty clear to you that the first fixed point is a stable fixed point. It's an attractor. The flow is moving towards the fixed point. The second fixed point is a repeller. It's an unstable fixed point. The flow is moving away from the fixed point. Now, using this information, you should also be able to draw x versus t diagram. Briefly, plot time on x-axis and x on y-axis. Now, when you are drawing these diagrams, x versus t diagrams, I encourage you to make sure that you take points in neighborhood of each fixed point. So, on left side of the first fixed point, on the fixed point, right side of the first fixed point. Similarly, immediate left of the second fixed point, on the fixed point, and the right side. Also, if there is a peak in your graph, a good idea is to take the initial value where the peaks or the lows of your plot are. So, using this information, you can very easily plot. Minus 2 is a stable fixed point, so it will be attracting the flow towards it. Plus 2 is an unstable fixed point, so the flow will be moving away from this. So, let's do this now. Let's start from the left side of minus 2. So, we are starting at a value slightly lower than minus 2. Notice dx by dt is positive. So, what's happening? The value of x will increase. It will move towards plus infinity, towards minus 2. And as it does that, dx by dt will continue to slow down because the magnitude of dx by dt is slowing down. So, if I start here, I will start moving like this and then slow down as the value approaches x equal to minus 2. Now, let's start from minus 2. If we are starting at minus 2, we stay at minus 2 because it is a fixed point. Now, let's start on the right side of minus 2. So, we are the x is slightly lesser than minus 2. So, we are starting here. Here, the dx by dt is negative. So, the flow will be towards left side, which means x is reducing. As x approaches minus 2, the magnitude of dx by dt reduces. So, the curve will look like this, a flat curve. Let me clean up a little bit because I want to introduce another term. Now, let's start at the center where x equal to 0. Look at it, x equal to 0, dx by dt is negative. It's also the maximum value of dx by dt. Appears to be, this is qualitative approach, we can't be sure, but it appears to be a pretty big value. So, when we are starting at x equal to 0, there is a rapid decline in the value of x, and as it declines and approaches minus 2, the magnitude of dx by dt starts reducing. So, the decline starts slowing down, and we again, as the x approaches minus 2, it starts becoming tangential to the horizontal line at minus 2. Now, let's start on the left side of plus 2. So, we are starting here. Dx by dt is negative, x is reducing. So, here if you are starting, we are reducing. Now as x reduces, as the flow moves towards left side, first the magnitude of dx by dt is increasing. So the slope will become more and more rapid, more and more steep. Now as it approaches 0 or the center of this curve, the peak of this curve, it will be the most steep. And then as x reduces in the negative range, going below 0, dx by dt is still negative, but the magnitude of dx by dt starts reducing. So the slope will start reducing and it will behave like others. So this is the kind of flow we expect. First, the rate at which x is reducing increases, deceleration increases, and then it starts slowing down. Now let's start on the right side of plus 2. So we are starting here at right side of plus 2. At right side of plus 2, dx by dt is positive. So we are moving here. The slope is positive. X is increasing. And as x increases, dx by dt increases. So the flow moves like so. X continues to increase. As it increases, the slope of this curve also continues to increase. What happens if we are starting at plus 2? If we are starting at plus 2, we remain at plus 2 because plus 2 is a fixed point. So this is how your curve looks like. Now if you see, I have been using the word flow in past few lectures to explain or to give you an indication of the direction in which x is moving, x is changing. When we draw plots like this, you can draw what are known as flow lines or slope lines. So I want to give you an idea of how they look when you use a modeling software like MATLAB, MathWorks, Octave or R. I am using dashed line to distinguish them from the trajectories we have drawn. So you see these lines occupy the entire x versus time diagram. So no matter where you are starting on this y-axis, you can always trace a flow line and figure out how the motion will be. So in one of the lectures in next week, I am going to actually use a model and show you how to draw slope lines using the software we have available with us. Now let's take another example. So the third example that I am going to take is dx by dt is equal to x minus x cube. And in this example, I am only going to draw the phase portrait and leave it up to you to figure out how x is changing with time. So once again, we have a linear part of this system and we have a cubic part of the system. So what you can do is you can factorize this and now figure out for what values of x will dx by dt be equal to 0. Now if you remember your basic mathematics, when x is equal to 1 or plus minus 1 or 0, dx by dt will be 0. So now in this case, how many fixed points do you have? You have 3 fixed points. The second step, if you remember, is to draw the phase portrait and figure out the stability of the fixed points. So let's draw the phase portrait. On x-axis, we put our only variable. This is a one-dimensional system. On y-axis, we put the rate at which this variable is changing, dx by dt. We know dx by dt will be 0 at these 3 fixed points. So we plot the fixed points first, minus 1, plus 1 and 0. So these are our fixed points. Now we need to draw the plot. So if you remember from previous example, we need to figure out what is the sign of the plot between and around the fixed point. So let's say x is much less than minus 1. So you can do one thing, you can take a value of x which is much less than minus 1. So let's say minus 2. So if you put in x equal to minus 2 in this, what you get is minus 2 minus minus 2 cube, and you will get a value which is bigger than 0. So you know here it is positive. Similarly, you can find that here it is negative between minus 1 and 0. Now what happens between 0 and 1? You can take a value of x between 0 and 1 and then figure out what the sign would be, and the sign will be positive, and here again it will be negative of the plot. So your plot looks like this. Now it should be, excuse me, this should be smooth. So I'll redraw this part. So now we know how our graph looks like, and this part is smooth, just to keep that in your mind. It's a continuous function. Now let's draw the arrows. Negative means dx by dt is negative, which means it's flowing towards left side. Positive, flow towards right side, towards plus infinity, left side, right side. By now, you know how to find the stability. This is an attractor. It's a stable fixed point. This is a repeller. So we leave an open circle around it. This is an attractor. So we close this circle. Now using this, you can plot x versus t diagram to figure out how x is changing with time. Remember, for your exams and also for your personal career, your practice, when you draw x versus time diagram, whether it is one-dimensional model, two or three-dimensional model, remember to cover the initial conditions around each fixed point, okay? Because the behavior might vary slightly, and it's very important to cover all of them. Even if you don't cover what's the behavior in the center between the two fixed points, it's important to be at least understanding of how the flow happens around the fixed points. Okay, now I'm going to give you an example of a chemical equation where we can apply the very simple principles we have studied so far to understand how the reaction is proceeding and to understand how to optimize the reaction. And the example I'm going to give is the example of autocatalysis. So, autocatalysis is when a substrate catalyzes its own production. So, it will look like this. There is a substrate A which we are trying to produce from raw product X, and it catalyzes its own production to A. This is autocatalysis. Now let's assume that X is available aplenty. It's available in enough quantity. That's not a limitation for us. What we are going to do is we are going to understand the rate at which A is being produced. So if you remember the basic chemical kinetics, you can write that dA by dt is equal to rate of forward reaction minus the rate of backward reaction. So I'm just going to write forward reaction minus the rate of backward reaction. So what it looks like, forward reaction you will get by this, K1 A into X, where the square bracket represent molarity, K1 is your reaction constant, minus backward reaction, so you have K2 A square, right? So now you are left with an equation which looks like this. I am going to get rid of the square bracket, understanding and assuming that you know that we are dealing with standard notation and standard units. Now remember, I said X is available in plenty, which means X is fairly constant. So our equation becomes simpler. Now this is a one-dimensional, very simple system. And we are going to use graphical approach to understand how it behaves. Remember, the first step is to find the fixed points. To find the fixed point, you need to find out when your dynamic term, your rate term becomes 0. So you need to find out when K1Ax minus K2A square is equal to 0. So for this, you may choose to factorize, which is what I would recommend. So you take A common, and then you have K1x minus K2A is equal to 0. So you have two fixed points. One is A is equal to 0, and the other is K1x by K2. K1 and K2 are reaction constants, so they are constant, and X is available aplenty. So you can even replace X by a number or the concentration, which will tell you about the concentration of X. You have two fixed points. Let's figure out the stability of the fixed points. So what we are going to do, we are going to draw the phase portrait. So on x-axis, we are going to put A, which is the variable. On y-axis, we are going to put the rate at which A is changing, dA by dt. We have two fixed points, so let's put it here, 0. Reaction constants are always positive, so K1 and K2 are positive. X is the concentration of the substrate which is present aplenty. It's a constant. It's available aplenty and it's also a constant. So all the terms here are positive. The product and the division will also be positive. So the second fixed point, which is K1x by K2, is here. It's a positive number. Now what we need to do is understand how the plot behaves, whether it is going to move like this or whether it's going to move like this. And the way we are going to figure out is look at the sign of dA by dt from minus infinity to 0, between 0 and the fixed point, second fixed point, and then when it is bigger than the second fixed point. And what we'll see is the graph looks like this. Now let's look at the direction of the flow. This is your first fixed point. Around the first fixed point, on the left side, dA by dt is negative. It means that the flow is moving towards minus infinity. The value of A is reducing. On right hand side, dA by dt is positive, which means the flow is towards right side. On right side of the second fixed point, dA by dt is negative, which means the flow is towards left side. Looking at the arrows around the fixed point, you can figure out that the first fixed point, which is 0, is an unstable fixed point. The second fixed point is a stable fixed point. Look, both arrows are pointing towards, which means if there is any perturbation around the second fixed point, the value will come back to this. Now using this information from the phase portrait, you can already start getting an idea of how autocatalysis works. How does it work? First of all, A can never be negative because it is concentration, so we can disregard anything on the left hand side of the y-axis. So let's look only at the right hand side of y-axis. On the right hand side of y-axis, as long as your starting concentration is between the two fixed points, not 0, between the two fixed points, A will continue to increase until it reaches K1x by K2. When it does that, it will stay there because it's a fixed point. If your starting concentration is beyond the second fixed point, which is K1x by K2, dx by dt is negative, which means the concentration of A will reduce until it reaches a fixed point. So, on the right side, the value reduces until it reaches K1x by K2. On left side, the value of A, the concentration of A increases until it reaches K1x by K2. Look here, x is a constant. K1 and K2 are universal constant under given temperature, pressure and conditions. So, how do we increase the productivity of A? If you are an industrial or chemical engineer and you want to increase the productivity of A, how do you use this qualitative diagram to figure it out? First, you can, no matter at what concentration of A you start, whether you start with low concentration or high, as long as there is sufficient A, it's not limiting nutrient, limiting concentration, limiting compound, you're going to end up at K1x by K2. What you can do is, you can shift K1x by K2 to the right side. You can make it bigger. How do you make it bigger? If you can change your reaction conditions to increase K1 or to reduce K2, or you can increase the value of X. So, even just by doing this much analysis, you can get an understanding of how to make the production of A more efficient, more productive for you. Now, what I want you to do is take some time to plot A versus time diagram for different initial condition. When A is quite small but still positive, when there is a decent A but initial amount of A, but it is less than, it is between the two fixed point, and then when A is starting, the starting concentration of A, molarity of A is beyond this fixed point. Now, if you remember logistic curve, this curve actually resembles logistic equation. In some way, K1x by K2 resembles the carrying capacity. We'll end here, and in the next lecture, I'm going to show you how to draw A versus time diagram for autocatalysis and how it, even without drawing it, the conclusions we have made are relevant for it. Thank you very much. See you in the next lecture.